Welcome to solverfy.
So we have a non-conducting material which has charge density rho, and we have a conducting material with surface charge density sigma. Now we have, as a Gaussian surface, let's consider a cylinder that looks like this. Now before we go ahead, remember that as an infinite plane or charge has field that is perpendicular to it because of symmetry. Similarly, in this case, we expect the charge to be horizontal. Also, notice that because of this charge sigma, the field on both directions will on both sides of it will be the same. And similarly, the field due to this charge distribution rho will also be the same on both of its sides, which means the electric field will be symmetric across this charge distribution. Now, let's find the electric field. On the left side. So let's say the electric field here is E. We expect the electric field to be E over here too. Now this is our origin, 0. Now the width of this non-conducting charge distribution is D. So, and we know that the electric field is perpendicular to this curved surface. So the flux there is 0. Hence the flux will only be through the two circular surfaces. That is 2 phi circular. And this will be equal to charge enclosed divided by epsilon naught. Now here the charge enclosed has two contributions, one from the surface charge density and one from the volume charge density. The surface charge density will give you a charge of sigma A, where A is the area of this cylindrical surface, of this circular surface. Plus we have charge distribution, charge from the volume distribution that will correspond to rho times volume of this cylinder, which will be D into A divided by epsilon naught. Now this is equal to E into the flux, which is, now we know that this is equal to 2 into phi through the circular surface, and we know that the flux through circular surface will simply be E times the area. So that is equal to sigma A plus rho dA by epsilon naught, which means E will be equal to sigma plus rho d by 2 epsilon naught. Now for part B, we want to find the field on the other side, and using the symmetry condition, as we've already argued, the electric field will be the same, except for the direction. In the first case, it will be leftwards, whereas in the second case, it will be rightwards. Now, for part C, we want to find out the charge inside the non-conducting charge material. So this is our center origin. Now let's say we have, let's not use this as our origin. Let's say this distance is x and we want to find the field here. So we'll consider a cylindrical surface that ends here. Now we already found the electric field on this surface. We know that this electric field here is sigma plus rho d by epsilon 2 epsilon naught. Let's say the electric field here is E dash. Now we use the same method. The flux will be equal to the flux through this surface plus the flux through this surface. The flux through the left surface will simply be sigma plus rho d by 2 epsilon naught into A, and the flux through the second surface will be E dash A. Now this is equal to charge enclosed divided by epsilon naught. Now the charge enclosed, as we would expect, would have again two contributions. The surface charge would give you sigma A, whereas the volume charge would give you rho times the volume, which would be AX. Hence, sigma plus rho d by 2 epsilon naught A plus E dash A will be equal to sigma A plus rho AX by epsilon naught, giving us E dash is equal to, notice that the area can be cancelled out and we'll also lose, and this gives us sigma plus rho into 2x minus d by 2 epsilon naught. This will be our electric field on the right surface inside the charge distribution.